Picture this: a lone spacecraft, gliding silently through the void between stars, carrying the first human travelers beyond our solar system. The light of our sun has faded to a faint point in the distance, and ahead lies only the unknown, a vast darkness punctuated by distant, unfamiliar suns. This isn't science fiction anymore. Humanity stands on the brink of an era where interstellar travel could become reality, and the theories that might unlock this incredible future are more thrilling than anything we've dreamed up in stories. For centuries, the idea of crossing the immense distances between stars seemed impossible, a fantasy reserved for novels and movies. The nearest star system, Alpha Centauri, is 4.37 light-years away. That's over 25 trillion miles. Even with our fastest spacecraft, it would take tens of thousands of years to get there. But what if we're closer than we think to cracking the code? What if, hidden in the minds of brilliant scientists and woven into the fabric of physics itself, are the ideas that could finally propel us beyond our cosmic backyard? That's exactly what we're about to explore: 30 groundbreaking theories that could redefine interstellar travel. Some involve harnessing the power of antimatter, others propose bending space-time itself, and a few dare to imagine technologies so advanced they border on magic. Each one represents a possible path to the stars, a potential key to unlocking humanity's greatest adventure. By the end of this journey, you'll not only understand these ideas, you'll feel the awe of realizing that one of them might just be the future. So buckle up, we're about to dive into the science, the speculation, and the sheer wonder of how humanity could take its first steps toward the stars. What if the secret to interstellar travel isn't about going faster, but about bending the very fabric of the universe instead? That's the revolutionary idea behind the Alcubierre Warp Drive, a concept so daring it could rewrite the rules of space exploration. Proposed in 1994 by physicist Miguel Alcubierre, this theory suggests a way to bypass Einstein's speed limit, the unbreakable law that nothing can travel faster than light. Instead of pushing a starship through space, the Alcubierre Drive would manipulate space-time itself, creating a ripple that carries the ship like a surfer riding a cosmic wave. Here's how it works. Imagine space as a stretchy fabric. The drive would compress space in front of the ship while expanding it behind, forming a moving bubble of warped space-time. Inside this bubble, the ship wouldn't actually move. Space itself would do the moving around it. That means no crushing G-forces, no time dilation, and theoretically, no violation of relativity. You could cross light years in what feels like weeks or even days, all while sitting comfortably in zero gravity. But there's a catch. To create this warp bubble, you'd need something called exotic matter, a hypothetical substance with negative energy density. Unlike normal matter, which gravity pulls, exotic matter would repel, propping open the warp bubble like an invisible scaffold. The problem: we've never observed exotic matter in nature, and producing it would require energy densities beyond anything we can currently harness. Some calculations suggest it might take the entire energy output of a star just to power a single warp jump. Then there's the question of stability. Even if we could generate exotic matter, maintaining a warp bubble without it collapsing mid-flight, or shredding anything in its path with lethal radiation remains a huge theoretical hurdle. Some physicists argue that the bubble's edges could accumulate dangerous particles over long distances, turning the ship's arrival into a cataclysmic event. Others speculate that creating a warp drive might require not just exotic matter, but an entirely new understanding of quantum physics. Yet for all its challenges, the Alcubierre Drive isn't just sci-fi. NASA Eagleworks Lab has conducted preliminary experiments, and researchers continue to refine the math, searching for ways to reduce the energy requirements or find loopholes in the equations. The dream persists because the alternative, spending centuries crawling between stars, feels unthinkable. After all, if humanity's future lies among the stars, we'll need more than just speed. We'll need to bend the universe to our will. While the Alcubierre Drive offers a tantalizing glimpse of faster-than-light travel, the road from theory to reality is littered with obstacles that could take centuries to overcome. Take the energy problem. Early calculations suggested the drive would require the equivalent of Jupiter's mass converted entirely into energy just to propel a modest-sized ship. That's not just impractical, it's laughably beyond our current capabilities. Even with refinements like physicist Harold White's work at NASA are suggesting a more donut-shaped warp bubble could reduce energy needs, we'd still require staggering amounts of power. Perhaps the output of multiple nuclear reactors compressed into a space no bigger than a car engine. Then there's the elephant in the room, exotic matter. This isn't just rare or hard to produce, it might not exist at all. The stuff defies normal physics, possessing negative mass that would push rather than pull under gravity's influence. Think of it like trying to build a bridge out of a material that repels nails instead of holding them. Some theorists argue quantum phenomena like the Casimir effect, where empty space subtly pushes objects together, might hint at ways to simulate exotic matter's properties. Others suggest manipulating dark energy, the mysterious force accelerating the universe's expansion. But these are speculations, not blueprints. The challenges don't stop there. A functioning warp drive could unleash unintended consequences. Crossing the boundary of a warp bubble might expose anything nearby to lethal levels of radiation. Imagine a starship arriving at its destination only to sterilize the planet it was meant to explore. There's also the terrifying possibility of causality violations where time itself gets tangled. If you can outpace light, you could theoretically arrive before you left, creating paradoxes that make physicists shudder. Yet research hasn't stalled. Beyond White's refinements, teams are exploring scaled-down lab experiments using laser pulses to mimic tiny warp bubbles. The idea isn't to build a starship tomorrow, but to nudge the math from blackboard scribbles toward testable physics. Private initiatives, like the Applied Physics Group's warp drive designs, argue that advancements in metamaterials, engineered substances with unnatural properties, could one day replicate exotic matter's effects. And then there's the wild card, discoveries we haven't even imagined yet. A century ago, nuclear fusion seemed as fantastical as warp drives do today. The universe has a way of surprising us. What makes these hurdles fascinating is their sheer scale. They're not just engineering problems, but fundamental questions about reality itself. Solving them would require rewriting textbooks, not just building better rockets. And that's the allure. The Alcubierre Drive isn't just a transport technology. It's an invitation to peel back the layers of the cosmos and ask, how much of the impossible is just physics we haven't mastered yet? Imagine a city floating between the stars, not just a spacecraft, but an entire self-sustaining world where generations of families are born, live, and die, all while inching closer to a distant planet their ancestors may never see. This is the stark reality of generation ships, a slower but more tangible path to the stars that trades warp drive's flashy speed for the patient, relentless march of time. While the Alcubierre Drive bends physics to its will, generation ships embrace the universe's vastness head-on, accepting that some journeys are too long for a single human lifetime. The math is sobering. Even reaching our closest stellar neighbor, Proxima Centauri b, a potentially habitable exoplanet, would take roughly 6,000 years with current propulsion technology. That's longer than recorded human history, but here's the twist: we wouldn't need breakthroughs in exotic physics to make it happen. Generation ships rely on technologies we already understand: closed-loop life support, hydroponic farming, artificial gravity, just scaled to unprecedented levels. Organizations like Icarus Interstellar have drafted blueprints for these cosmic arcs, envisioning rotating habitats with forests, rivers, and even simulated seasons to mimic Earth's rhythms. The ship itself becomes a fragile egg cradling civilization across millennia. Yet the challenges aren't just technical, they're deeply human. How do you maintain societal cohesion when the mission's purpose fades into myth? Would ship-borne generations raised in metal corridors under artificial suns still care about a planet they've never seen? History offers grim warnings. Isolated communities, from submarine crews to Antarctic researchers, often fracture under stress, and a generation ship's isolation would dwarf anything humans have endured. Mutinies, cultural drift, or even the loss of critical knowledge over centuries could doom the mission silently, leaving the ship adrift as a tomb. Ethical dilemmas loom just as large. Is it fair to condemn unborn generations to a life of confinement, with no choice but to uphold their ancestors' ambitions? Some argue it's no different than raising children in remote Alaskan villages or space stations, just with fewer exit options. Others compare it to a benign form of slavery, where every newborn's destiny is predetermined by a decision made centuries earlier. And what if the destination world turns out to be uninhabitable? After 6,000 years of voyage, there's no turning back. Psychological studies of long-term space habitation hint at the strain ahead. NASA HIC's Mars simulations show how even tight-knit crews buckle under monotony and close quarters. Now amplify that over hundreds of generations, without radical advances in cryosleep or life extension, generation ships demand something extraordinary, a redesign of human society itself. Perhaps the answer lies in embracing the voyage as the goal, not a means to an end, but a new way of living among the stars. After all, if Earth ever becomes uninhabitable, these slow arcs might be our only chance to survive. They're not just ships, they're lifeboats for the species. Keeping thousands of people alive for centuries in the void of space isn't just about building a bigger rocket. It's about recreating Earth's fragile web of life inside a metal hull. That's the monumental challenge of closed-loop life support systems, where every breath of air, every drop of water, and every scrap of waste must be endlessly recycled. Picture a high-tech ecosystem where microbes break down human waste into fertilizer for crops. Those crops purify the air by converting carbon dioxide to oxygen, and condensation systems capture every exhaled vapor. One small failure, a fungal bloom in the hydroponic trays, a glitch in the algae bioreactors, could cascade into catastrophe over decades. Biosphere 2 taught us just how delicate this balance can be. In the early 1990s, 8 researchers sealed themselves inside a 3-acre glass habitat in the Arizona desert, attempting to mimic Earth's ecosystems. Within months, oxygen levels plummeted as unexpected soil bacteria devoured the air. Coffee became a black market commodity, and factions formed over farming practices. Yet this cramped experiment lasted only 2 years, a blink compared to a generation ship's voyage. Scaling these systems for millennia would require technology that doesn't just recycle resources, but anticipates thousands of unforeseen variables. Imagine AI-driven ecosystems constantly adjusting pH levels in aquaculture tanks or predicting mutations in staple crops before they endanger the food supply. Then there's the question of what to grow. Hydroponic farms aboard a generation ship wouldn't just feed bodies, they'd need to feed souls. Early space station menus packed with freeze-dried gruel caused astronauts to lose weight simply from boredom with eating. Future ships might cultivate emotional staples, strawberry patches for birthdays, basil and mint to combat the sterile scent of recycled air. Vertical farms could rotate crops not just for nutrition, but to simulate Earth seasons, offering psychological relief from the monotony of metal corridors. Some designs even incorporate micro-livestock quail for eggs, crickets for protein, though the line between sustainable protein source and beloved pet quickly blurs in isolation. But the hardest system to engineer won't be made of pipes or plants, but of people. Long before supplies run low, social fractures could doom the mission. Anthropologists studying confined groups from nuclear submarine crews to Antarctic research stations find that small tensions magnify over time. On a generation ship where dissenters can't quit and children never chose the mission, maintaining stability might require radical cultural innovations. Perhaps ship-borne generations would develop their own religions venerating the voyage as a sacred journey, or governance systems that rotate power through family lineages. Others suggest artificial intelligence could arbitrate disputes, though handing ultimate authority to machines carries its own risks. The most haunting lesson from Biosphere 2 wasn't technical but human. When one researcher deliberately sabotaged equipment to force early termination, it revealed an uncomfortable truth. No life support system can compensate for the unpredictability of human nature. A generation ship's real engines won't be its thrusters, but the unbroken will of thousands who have never known Earth, yet keep steering toward a world they'll never see. Their survival would depend on something far more fragile than technology, a shared story compelling enough to last 6,000 years. What if the key to surviving a centuries-long journey to the stars isn't building faster ships, but simply pressing pause on life itself? Cryogenic suspension, once the stuff of pulp sci-fi, is now a serious field of research, offering a chillingly elegant solution to the problem of interstellar travel. Freeze the crew, halt their biological clocks, and wake them centuries later when the ship arrives. It sounds like magic, but the science behind it is already taking shape in labs today. The concept hinges on a process called vitrification. Unlike freezing, which turns tissues into jagged ice crystals that shred cells, vitrification uses cryoprotectant chemicals to transform the body into a glass-like state at ultra-low temperatures. Think of it like preserving a delicate insect in amber. Molecular activity grinds to a near halt, but the structure remains intact. Companies like Alcubierre Life Extension Foundation have already vitrified hundreds of clients, storing them at -196 degrees Celsius in the hope that future medicine might one day reverse the process. Their focus, preserving the brain's neural connections, the seat of memory and identity, even if the rest of the body requires regeneration. But the hurdles are as formidable as the promise is tantalizing. Reviving a vitrified organism isn't just warming it up, it's navigating a minefield of cellular damage. Even with cryoprotectants, tissues can fracture during cooling, and the chemical cocktails themselves can be toxic. Experiments with small organisms like nematode worms and rabbit kidneys have shown limited success, but scaling up to humans is like comparing a puddle to an ocean. Then there's the brain, the ultimate challenge. Neurons are exquisitely delicate, their trillions of synapses encoding everything that makes a person them. A single misstep in preservation could mean losing decades of memories, or worse, awakening as a stranger in one's own mind. Ethical dilemmas lurk in the cold just as much as technical ones. Who decides when to revive the crew? An AI captain programmed for caution might wait until the ship reaches Proxima Centauri's orbit, but what if sensors detect an emergency en route? And how would interstellar travelers cope psychologically, waking to a future where everyone they knew is centuries dead? Some propose periodic thaw cycles, where crews revive in shifts to check systems, but each freeze-thaw cycle risks cumulative damage. There's also the unsettling possibility of being revived in a world where the mission no longer matters. Imagine waking only to learn Earth scientists perfected warp drives 50 years after your ship launched. Yet research marches forward. Breakthroughs in nanotechnology suggest microscopic machines could one day repair cellular damage during revival. The field of cryobiology is exploring how Arctic frogs and tardigrades survive natural freezing, mining their biology for clues. And startups like Timeship aim to make cryonics mainstream, envisioning orbital memory palaces where thousands wait in cold storage for medical breakthroughs. The math is seductive. Freeze a crew and a 1,000-year voyage becomes a single night's sleep. No generation ships, no warp drives, just the quiet hum of refrigeration units keeping hope alive in the dark. But perhaps the most profound question isn't whether we can freeze travelers for the stars, but whether we should. Cryogenic suspension doesn't just challenge our technology, it challenges our very definition of life and death. Is a frozen astronaut merely a very patient corpse or a pioneer in suspended animation? The line blurs, and that ambiguity might be the price of reaching the stars without breaking the laws of physics. For now, the dream remains on ice, waiting for science to tip the scales from speculation to reality. The moment of revival is where cryogenic dreams collide with biological reality. A frozen astronaut isn't just a puzzle to reassemble, but a race against time as warming tissues face new dangers. Recent breakthroughs in cryopreservation offer glimmers of hope, like the successful thawing of a vitrified rabbit kidney that later functioned when transplanted. The trick, nanotechnology. Scientists are engineering microscopic anti-ice particles that prevent crystal formation during rewarming, while artificial capillaries could one day flush cryoprotectants from thawing organs without damaging delicate cells. For interstellar travelers, this could mean waking up not to a scarred, fragile body, but one as healthy as the day it was frozen. Yet organs are simple compared to the brain's labyrinth of memories and personality. Even slight damage during revival could alter someone's very identity. Imagine waking to find your childhood memories frayed at the edges, or your emotional responses subtly reshaped. Some researchers propose bypassing the problem entirely by scanning preserved brains and uploading consciousness into digital or synthetic bodies. Projects like Neuralink's brain-computer interfaces hint at the possibility of decoding neural patterns, while quantum computing could one day simulate a human mind's staggering complexity. The allure is obvious. Why risk reviving a fragile biological body when you could exist as invincible code, traveling between stars as pure information? This idea sparks fierce ethical fires. Would an uploaded consciousness truly be you, or just a copy with your memories? Philosophers call this the continuity of self problem. If your frozen brain is scanned and activated in a machine, is that machine you, or a digital twin that believes it's you? The original biological you might still lie frozen, unaware. Worse, what if uploads can be edited or duplicated? A crew member could wake to find 10 digital versions of themselves arguing over who's the real one. Practical hurdles abound too. Even if we could perfectly map a brain's 86 billion neurons, replicating their quantum-level interactions may require computers more advanced than anything we've conceived. And how would uploaded minds experience time during centuries of travel? A digital consciousness could theoretically speed up its perception, making the journey feel like minutes, but that isolation might drive it mad. Meanwhile, cryobiologists counter that biological revival, for all its risks, preserves the messy, beautiful continuity of organic life. The debate crystallizes a deeper question: is interstellar travel worth sacrificing humanity itself? Uploading might solve the body's fragility, but at the cost of becoming something other than human. Conversely, betting on cryogenic revival means accepting that some pioneers may never wake, or may wake irrevocably changed. Between these two futures lies a third path. Perhaps the solution isn't choosing one, but pursuing both, letting explorers decide whether to risk their biology or their identity in the great dark. After all, the stars don't care how we reach them, only that we dare to try. Sometimes the most audacious ideas in science sound like something ripped from an action movie, and few are as explosively bold as nuclear pulse propulsion. Picture this: a massive spacecraft with a giant pusher plate at its rear, riding a continuous hailstorm of atomic detonations to propel itself forward. This wasn't just a wild thought experiment, it was a real, funded project in the 1950s called Orion, championed by physicist Freeman Dyson. While most rocket designs rely on controlled burns of chemical fuel, Orion threw subtlety out the airlock. Its philosophy, go big or go home. The mechanics were as brutal as they were brilliant. Small nuclear bombs, each packing roughly the punch of the Hiroshima blast, would be ejected behind the ship and detonated. The resulting plasma fireball would slam into the pusher plate, transferring momentum through a series of hydraulic shocks. A system of shock absorbers would smooth out the ride, turning what sounds like a cosmic jackhammer into something resembling steady thrust. Calculations suggested this could theoretically accelerate a ship to 5% the speed of light, fast enough to reach Alpha Centauri in under a century. Compared to the glacial pace of generation ships or the speculative physics of warp drives, Orion offered something tantalizing, a near-term path to the stars using existing technology. But the devil lurked in the fallout, literally. Each detonation would drench the ship in radiation, requiring heavy shielding to protect the crew. Even then, prolonged exposure might be unavoidable. Then there's the small matter of launching hundreds or thousands of nuclear devices into space, any one of which could accidentally detonate during ascent, turning the launch site into a radioactive crater. Environmental and political concerns ultimately doomed the project. The 1963 Partial Test Ban Treaty, which prohibited nuclear explosions in space, pulled the plug on Orion before prototypes could advance beyond small-scale, conventional explosive tests. Yet the idea never fully died. Later studies refined the concept, proposing cleaner nuclear charges or magnetic shielding to contain radiation. Some even speculated about antimatter-triggered pulses for greater efficiency. The core appeal remains. In a universe where energy equals speed, nothing packs more raw energy per kilogram than nuclear fission. Orion's legacy is a reminder that humanity's reach for the stars might not always be graceful. Sometimes it's a chain reaction of fire and thunder, pushing us forward one explosion at a time. Decades after the original Orion project faded, its spirit lives on in modern adaptations that strip away the radioactive stigma while keeping the raw power of nuclear propulsion. One of the most promising is the nuclear saltwater rocket, a design so audacious it feels like alchemy. Instead of detonating atomic bombs, this engine would pump a solution of uranium or plutonium salts into a reaction chamber where the mixture becomes spontaneously critical. The result, a continuous, controlled nuclear explosion channeled through a nozzle, generating thrust far more efficient than chemical rockets. It's like turning a wildfire into a welder's torch, harnessing chaos with precision. The advantages are staggering. A nuclear saltwater rocket could theoretically reach 5 to 10% the speed of light, slicing interstellar travel times to mere decades. Unlike Orion's bomb-based approach, there's no risk of accidental detonations during launch, since the fuel only becomes reactive in the engineered environment of the chamber. And because the reaction stops the moment the fuel flow cuts off, it's inherently safer than solid core nuclear designs, but don't mistake safer for safe. The exhaust would still be a plume of superheated radioactive steam, making this a strictly space-bound technology. Any mishap in Earth's atmosphere could rain fallout over continents. Meanwhile, NASA's Innovative Advanced Concepts program has been quietly funding research into pulse fission systems that borrow Orion's logic but shrink it to a less apocalyptic scale. Imagine tiny, self-contained nuclear charges no bigger than a grapefruit detonated in rapid succession, their energy captured by advanced magnetic nozzles. These micro-explosions would trade the brute force of Orion for surgical efficiency, reducing radiation leakage and eliminating the need for massive shock absorbers. Early simulations suggest such a system could propel a probe to Mars in weeks, not months, hinting at its potential for interstellar precursors. The real game changer, though, might lie in fusion pulses rather than fission. Projects like Princeton's direct fusion drive aim to create compact, steady-state fusion reactors, but some theorists propose pulsed fusion as a middle ground. By zapping pellets of deuterium with lasers or particle beams, a process already tested in lab-scale inertial confinement experiments, each microexplosion could generate clean, high-energy thrust without long-lived radioactive waste. It's the difference between burning coal and igniting hydrogen. Same basic principle, radically different consequences. What unites these modern twists on Orion is their refusal to accept light speed as an unbreakable barrier. They embrace nuclear energy not as a last resort, but as the only known power source dense enough to propel humans across interstellar distances within a lifetime. The challenges remain formidable: radiation shielding, fuel handling, political resistance, but the math doesn't lie. In a universe where energy equals speed, splitting atoms might be the least impossible way to reach the stars. Perhaps the most poetic irony is that these designs don't discard Orion's vision, they refine it. Where the original relied on Cold War-era megaton blasts, its descendants seek elegance in miniaturization and control. The dream hasn't changed to ride fire beyond the solar system. Only now the fire burns cleaner, brighter, and with the careful restraint of decades of hindsight. Among all the exotic propulsion ideas dreamed up by physicists, none pack the raw, terrifying power of antimatter. This is the universe's ultimate energy source, a substance so potent that a single gram could unleash the explosive force of a small nuclear bomb. Unlike nuclear reactions, which convert less than 1% of mass into energy, antimatter annihilates completely upon contact with normal matter, releasing 100% of its mass as pure energy according to Einstein's famous equation. For interstellar travel, that efficiency is game-changing. A spacecraft could reach half the speed of light with just kilograms of fuel, turning a trip to Alpha Centauri into a decades-long mission instead of a millennia-spanning odyssey. The principle is deceptively simple. When a particle of matter meets its antimatter counterpart, say, an electron colliding with a positron, they vanish in a flash of gamma rays. Harness that energy, and you've got a rocket engine unlike any other. Practical designs involve injecting antiprotons into a reaction chamber filled with normal hydrogen. The resulting annihilation creates charged particles that magnetic fields can direct out the rear as thrust. Some concepts even use the gamma rays themselves, bouncing them off a sail like absorber to transfer momentum. The numbers dazzle. Antimatter propulsion could deliver 10,000 times the energy density of chemical fuels and 100 times that of nuclear fission. But there's a catch that makes warp drives look almost conventional. Antimatter doesn't exist naturally in usable quantities. We have to create it ourselves, atom by atom, in particle accelerators like CERN. Currently, global production amounts to mere nanograms per year, enough to power a light bulb for a few seconds. Scaling up to the grams needed for interstellar travel would require unimaginable infrastructure. Even optimistic estimates suggest building continent-sized accelerator complexes powered by entire nuclear reactors, running continuously for centuries. The energy input would far exceed what the antimatter could later release, making it the universe's most inefficient battery. Then there's storage. Antimatter can't touch container walls without annihilating, so we trap it using electromagnetic fields in near-perfect vacuums. The slightest fluctuation, a power hiccup, a cosmic ray strike, could trigger catastrophic containment failure. Imagine a spaceship carrying several grams of antimatter suddenly losing magnetic confinement. The resulting explosion wouldn't just destroy the vessel, it'd outshine the sun for a fraction of a second. Some engineers propose storing antimatter as frozen antihydrogen or embedding antiprotons in inert materials, but these are untested gambles. The most promising near-term application might be hybrid systems. NASA Institute for Advanced Concepts has studied antimatter-catalyzed fusion, where tiny antimatter sparks trigger larger fusion reactions, reducing the antimatter needed by a factor of 1,000. Others propose harvesting naturally occurring antimatter from planetary magnetic fields. Jupiter's radiation belts, for instance, contain trace amounts of antiprotons. It's a long shot, but so was splitting the atom in 1942. What makes antimatter so compelling isn't just its physics, but its audacity. This is a technology that doesn't merely push boundaries, it annihilates them. Every hurdle from production to containment forces us to confront fundamental limits of engineering and cosmology. Yet the promise remains, if we can master antimatter, we won't just reach the stars. We'll tame the very energy of creation itself. Storing antimatter is like trying to cage lightning. The slightest mistake means instant annihilation. But recent breakthroughs in penning traps are turning this sci-fi nightmare into a solvable engineering puzzle. These devices use intricate magnetic and electric fields to suspend antimatter particles in a near-perfect vacuum, preventing them from touching ordinary matter. The most advanced traps can now hold antiprotons for months, a leap from the milliseconds possible just decades ago. CERN base experiment even achieved a world record by confining antimatter for over a year, using cryogenic cooling to near absolute zero. That's the difference between a flickering candle and a steady flame, a critical step for interstellar missions where fuel stability is non-negotiable. Yet penning traps have limits. They're energy-hungry, requiring constant power to maintain fields, and scaling them up to store grams of antimatter, let alone kilograms, would demand spacecraft-sized installations. That's where hybrid solutions like antimatter-catalyzed fusion come in. Physicist Stephen Howe's designs are particularly ingenious. Instead of relying entirely on antimatter annihilation, his microfusion drive uses tiny bursts of antiprotons to trigger larger fusion reactions in deuterium or helium-3. Think of it as using a match to ignite a bonfire. A single milligram of antimatter could initiate enough fusion events to propel a ship to Mars in weeks, or even reach nearby stars within a human lifetime. The beauty lies in efficiency. You're not just burning antimatter, but leveraging it to unlock vastly greater energy reserves. Howe's concept hinges on precision timing. Antiprotons are injected into a fuel pellet where they annihilate with normal matter, creating a shower of high-energy pions. These particles heat the pellet's core to fusion temperatures, sparking a reaction that releases far more energy than the antimatter alone could provide. It's a chain reaction with built-in safeguards. Unlike pure antimatter engines, a containment failure here would release only a fraction of the stored energy. NASA's Innovative Advanced Concepts program has explored similar ideas, with simulations showing potential thrust-to-weight ratios 10 times better than conventional fusion designs. The real kicker, this technology might not require wholesale antimatter production. Space-based collectors could harvest antiprotons from Earth's radiation belts or Jupiter's magnetosphere, where cosmic rays naturally generate trace amounts. While the quantities are minuscule, perhaps a billionth of a gram per year, even that could be enough for catalyzed fusion, turning a fuel scarcity problem into a logistics challenge. Combine this with advancements in portable penning traps, and suddenly, antimatter propulsion seems less like fantasy and more like a waiting game for engineering refinements. Of course, the hurdles remain Everest-sized. Magnetic confinement systems must become lighter and more power-efficient to fit aboard spacecraft. Radiation shielding would need to handle not just gamma rays from annihilation, but also neutrons from fusion. And the sheer cost of producing and storing antimatter, currently estimated at trillions of dollars per gram, demands breakthroughs in particle accelerator efficiency. Yet the vision persists because the alternatives pale in comparison. Chemical rockets are too weak, nuclear pulse propulsion is politically fraught, and warp drives remain speculative. Antimatter, for all its volatility, offers a path grounded in known physics. Perhaps the most tantalizing aspect is how these storage and catalytic techniques blur the line between energy and matter. Antimatter isn't just fuel, it's a key that unlocks other energy sources, compressing the power of stars into reactors small enough to fit on a spacecraft. Every nanogram securely stored, every fusion event successfully triggered, brings us closer to a universe where humanity doesn't just dream of the stars, but reaches them on pillars of controlled annihilation. Imagine a spacecraft with no engines, no fuel tanks, just an ultra-thin sail thinner than a soap bubble, riding a beam of light to another star. This isn't fantasy, it's the heart of breakthrough starshot, tech billionaire Yuri Milner's audacious plan to send the first human-made objects to Alpha Centauri within our lifetimes. The strategy flips traditional space propulsion on its head. Instead of carrying massive fuel reserves, featherweight probes weighing mere grams would be pushed by a 100-gigawatt laser array fired from Earth. Think of it as the ultimate cosmic slingshot. Light itself becomes the wind, and the sail, barely visible to the naked eye, becomes the vessel. The sail's composition is where materials science meets magic. Early prototypes use graphene or molybdenum disulfide materials just one atom thick yet stronger than steel. These aren't passive reflectors but engineered metamaterials designed to absorb specific laser wavelengths with near-perfect efficiency. When the laser barrage hits, photons transfer momentum to the sail, accelerating it to mind-bending speeds. Calculations suggest that a square sail 4 meters across, weighing less than a paperclip, could reach 20% the speed of light if the laser fires continuously for minutes. At that velocity, Alpha Centauri's 4.37 light-year distance collapses to a 20-year journey. A flyby mission would zip past Proxima Centauri b, snapping images and collecting data before streaming its findings back to Earth via a 1-watt laser, a whisper across the interstellar dark. But the engineering hurdles are as vast as the distances involved. Coordinating a laser array spanning kilometers to focus on a sail the size of a picnic table, already thousands of miles away and receding at relativistic speeds, demands precision beyond anything we've attempted. Atmospheric turbulence could scatter the beam, requiring adaptive optics systems that adjust mirrors in real time to compensate. Then there's the sail's survival. At acceleration, forces reaching 60,000 Gs, even atomic-scale imperfections could tear it apart. Dust grains or micrometeoroids, harmless to conventional spacecraft, would punch through the sail like bullets through tissue paper. Some designs propose spinning the sail to distribute stress or embedding self-healing nanomaterials, but these remain untested at interstellar scales. Communication poses another nightmare. The probe's tiny laser, with the power of a child's toy, must beam data across trillions of miles to receivers on Earth. Proposed solutions include deploying a network of relay satellites or using the sail itself as a parabolic antenna, but signal strength would still be weaker than a neutrino's whisper. Even the laser's power source is daunting. A 100-gigawatt array would require energy equivalent to dozens of nuclear reactors, pulsed in perfect unison, infrastructure incompatible with current power grids unless built in orbit or on the moon. What makes Starshot revolutionary isn't just the technology but the philosophy behind it. Instead of waiting centuries for breakthroughs in fusion or antimatter, it leverages existing physics in radical ways. The project's co-founder, physicist Philip Lubin, frames it as a massively parallel approach, launch thousands of probes to offset individual failures, embracing redundancy over perfection. It's the opposite of traditional space exploration's flagship mission mentality, more akin to dandelion seeds scattered on a stellar wind. Critics argue Starshot prioritizes speed over science. Gram-scale probes can't carry traditional instruments. Imaging might rely on diffraction lenses no wider than a pixel, and sensors would need revolutionary miniaturization. Yet supporters counter that the mission's value lies in proving interstellar travel is possible now, not centuries from now. even a single successful flyby would shatter psychological barriers, transforming Alpha Centauri from a distant dot to a reachable destination. The project's most subversive idea might be its timeline. While other interstellar concepts languish in theoretical purgatory, Starshot's team believes a working prototype could launch by mid-century, making its backers the potential Galileos of interstellar exploration. Whether they succeed or fail, their legacy will be undeniable, proving that humanity's first steps into the cosmos might not need monstrous rockets, but the quiet push of light against a sail thinner than a dream. Robert Forward, the visionary physicist who first proposed laser sails in the 1980s, imagined something far grander than gram-sized probes, a colossal, staged sail system capable of carrying humans. His design reads like something from an interstellar engineering manual, a primary sail hundreds of kilometers wide, made of diamond filament mesh to withstand the laser's blistering intensity. This sail wouldn't travel with the ship. Instead, it would act as a mirror, reflecting the beam toward a smaller secondary sail attached to the crewed vessel. The result, a chain reaction of light, bouncing between sails to multiply thrust while keeping the fragile human payload at a safe distance from the laser's fire hose of energy. The scale is staggering. A crewed mission would require laser arrays dwarfing anything on Earth. Think continent-sized installations orbiting the Sun, drawing power from vast solar farms or even Dyson swarms. Forward's calculations suggested accelerating a 1,000-ton Starship to 10% light speed would demand a laser with the output of a small star sustained for years. The sail alone would mass tens of thousands of tons, thinner than a razor's edge yet strong enough to resist tearing under forces that could shred steel. It's the ultimate megaproject, akin to building the Great Wall of China in space. But the real challenge isn't just engineering, it's diplomacy. A laser capable of propelling starships could also double as a weapon of unimaginable destructive power. A misfired beam or a slight miscalculation in targeting could slice through cities like a scalpel through paper. The politics of such infrastructure would be a minefield. Who controls the laser? What happens if rival nations or corporations vie for its use? Imagine interstellar road rage, where conflicting schedules for beam time lead to geopolitical standoffs or worse, sabotage. Some have proposed placing lasers around uninhabitable planets like Mercury as neutral ground, but the risk of weaponization would loom over every treaty negotiation. Then there's the question of braking. Unlike Starshot's flyby probes, crewed ships need to stop at their destination, a feat as difficult as the initial acceleration. Forward's solution was characteristically daring. Detach a section of the sail en route, letting it race ahead to reflect light back toward the ship, slowing it like a parachute catching wind. The precision required borders on absurd, with margins for error measured in meters across light years. One wrong calculation, and your starship becomes a high-speed meteor shower for whatever alien world you were hoping to colonize. Yet the allure persists. Laser highways could unlock a future where starships move like freighters on scheduled routes, their sails catching predictable beams like trains riding rails of light. Private ventures like Breakthrough Starshot hint at early economic models, beam time sold by the hour, propulsion as a subscription service. Others envision cooperative alliances pooling resources, turning laser arrays into cosmic lighthouses shared by all humanity. The vision is seductive, a network of light stretching across the galaxy, not unlike the trade winds that once connected continents on Earth. But perhaps the most profound implication of laser sails isn't technical or political, it's philosophical. Unlike warp drives or generation ships, this technology leaves an indelible mark on the solar system. Future archaeologists might find our first interstellar infrastructure not in scattered probes, but in the ruins of abandoned laser arrays, their silent mirrors still pointing toward the stars like the arrowheads of a civilization that dared to reach beyond the firelight of its sun. What if the vast distances between stars weren't barriers at all, but mere wrinkles in the cosmic fabric waiting to be smoothed out? Enter wormholes, the universe's hypothetical shortcuts. These tunnels through spacetime, formerly known as Einstein-Rosen bridges, emerged from Einstein's equations of general relativity nearly a century ago. Picture spacetime as a sheet of paper folded in half. A wormhole would be like poking a pencil through both layers, creating a bridge between points that would otherwise be centimeters or light years apart. It's not about moving faster than light, it's about redefining the map itself. The catch: naturally occurring wormholes, if they exist at all, would likely be microscopic, unstable, and collapse instantaneously. That's where physicist Kip Thorne's groundbreaking work comes in. In the 1980s, Thorne explored the idea of traversable wormhole structures that could theoretically allow human passage. His calculations revealed a bizarre requirement. To prop open a wormhole's throat against gravity's crushing force, you'd need exotic matter with negative energy density. Unlike normal matter, which curves spacetime inward, negative energy would bend it outward, acting like cosmic scaffolding to prevent the tunnel's collapse. Negative energy isn't entirely fictional. Quantum mechanics allows for fleeting instances of it, like the Casimir effect, where empty space between two metal plates exhibits measurable negative pressure. But scaling this up to stabilize a wormhole would demand amounts far beyond our current understanding, possibly the energy equivalent of multiple stars concentrated into a single structure. There's also the small matter of navigation. Even with a stable wormhole, traversing it might require precise tuning to avoid tidal forces that could spaghettify a traveler, or random exits that dump you into a black hole. Thorne's theories birthed some truly wild possibilities. A wormhole could link not just distant places but different times, effectively becoming a time machine. This raises paradoxes. What if you traveled back and prevented the wormhole's creation? That makes physicists question whether the universe would permit such structures to exist. Some speculate that quantum effects or undiscovered laws might actively prevent stable wormholes, acting as cosmic censorship to protect causality, yet the dream persists. Modern researchers are exploring alternatives like naturally occurring wormholes from the early universe, inflated to macroscopic sizes during cosmic inflation. Others propose that advanced civilizations might engineer them using technologies we can't yet fathom. After all, to a species that's mastered negative energy, wormholes might be as routine as subway tunnels. What makes wormholes so compelling is their audacity. They don't just bend the rules, they rewrite them. While warp drives twist spacetime around a ship and generation ships accept the grind of time, wormholes dismiss distance entirely. They're the ultimate cheat code for the universe, if only we could crack it. Until then, they remain a dazzling reminder that the cosmos might hold shortcuts we've yet to imagine, hidden doors in the fabric of reality, waiting for the right key. The quantum foam theory paints a wild picture of spacetime at the smallest scales, a seething, bubbling froth where tiny wormholes flicker in and out of existence like bubbles in a boiling pot. These hypothetical structures, predicted by quantum gravity models, would be unimaginably small, perhaps a billionth of a billionth the size of an atom. But here's the tantalizing part. If we could somehow capture and enlarge one of these quantum wormholes, stitching it open with exotic matter, we might engineer a traversable gateway to the stars. The problem: this foam exists at energies trillions of times beyond what our particle colliders can produce, placing it firmly in the realm of speculation for now. Recent experiments with the Casimir effect offer a faint glimmer of hope. When two ultra-smooth metal plates are placed nanometers apart in a vacuum, quantum fluctuations between them create measurable negative energy, the same kind needed to stabilize a wormhole's throat. While the amounts generated are microscopic, some physicists suggest that advanced nanotechnology could one day stack millions of these Casimir cavities like atomic-scale Lego blocks, amplifying the effect. It's like trying to dam a river with drinking straws, but the principle is sound. Quantum mechanics already allows for the raw ingredients of wormhole engineering. Now comes the brain-melting part. A stabilized wormhole wouldn't just bridge space, it could bridge time. Einstein's equations show that if one end of a wormhole is accelerated to relativistic speeds or placed near a black hole's gravity well, time dilation would cause the two ends to desynchronize. Return the moving end to Earth and you've created a time machine. Step through in 2040 and exit in 2030. The implications are dizzying. Want to witness the Cretaceous period? Just park one end near a neutron star for a few years while Earth's end ages normally. The wormhole becomes a tunnel not just through space but through history itself. But the universe seems to abhor such paradoxes. The Novikov self-consistency principle suggests any attempt to change the past would inevitably enforce events as they already happened. Your time travel actions were always part of history. Try to assassinate your grandfather, the gun jams, or you miss, or it turns out he wasn't your real grandfather after all. Quantum versions of this idea propose parallel timelines branching at each wormhole transit, sidestepping paradoxes by fracturing reality. Either way, the takeaway is unsettling. Wormholes might not just be interstellar shortcuts, but locksmith's tools for the prison of linear time. Practical hurdles remain Everest-sized. Stabilizing even a microscopic wormhole would require negative energy densities that might defy the laws of thermodynamics. Some theories suggest dark energy, the mysterious force accelerating the universe's expansion, could be harnessed, but we don't even know what dark energy is yet. Then there's the terrifying possibility of a wormhole collapsing mid-transit, stranding travelers in non-existence or splicing them across dimensions. Yet the mathematics refuses to dismiss the idea entirely. Wormholes linger at the edge of plausibility, teasing us with their Escher-like geometry. They represent more than just a transportation gimmick. They're a test of how deeply we can manipulate the universe's underlying code. Master them, and the cosmos becomes not a vast, lonely expanse, but a tangled web of connections waiting to be traced. The price of admission, nothing less than rewriting our understanding of physics itself. Black holes aren't just cosmic vacuum cleaners, they might also be the ultimate gravity slingshots for interstellar travel. Picture a starship skimming perilously close to a black hole's event horizon, using its monstrous gravitational pull like a galactic slingshot to fling itself across the galaxy at unimaginable speeds. This isn't just science fiction, it's a concept rooted in real physics, exploiting a phenomenon called the Oberth effect. Named after German physicist Hermann Oberth, this principle states that a spacecraft gains more kinetic energy when it fires its engines at high speeds, especially near intense gravitational fields. In simpler terms, the faster you're already going, the bigger the boost you get from a burst of thrust, and nothing accelerates you faster than a black hole's grip. The math is both elegant and terrifying. As a ship approaches a black hole, it's pulled into an ever-tightening spiral, reaching velocities that could approach a significant fraction of light speed. At the precise moment of closest approach, the periapsis, the ship fires its engines. The combination of its existing velocity and the black hole's gravity amplifies the thrust exponentially, potentially propelling the ship toward another star system. It's like jumping off a swing at the peak of its arc, only this swing is woven from the fabric of spacetime itself, but the margin for error is razor-thin. Venture too close and tidal forces will stretch the ship and its occupants into molecular spaghetti, a process literally called spaghettification. The difference between a perfect slingshot and a one-way trip into oblivion might come down to mere kilometers. Even a slight miscalculation in trajectory could send the ship spiraling past the point of no return, where not even light can escape. Some theorists suggest using rotating Kerr black holes, which twist spacetime around them, as slightly safer options. Their ergosphere, a region outside the event horizon where space itself is dragged into rotation, might allow for energy extraction without crossing the fatal boundary. Imagine a ship surfing the edge of this cosmic whirlpool, stealing momentum from the black hole's spin like a surfer catching a wave. The concept grows even wilder when paired with other technologies. A ship equipped with a Bussard ramjet, a theoretical engine that scoops up interstellar hydrogen for fuel, could use the black hole's gravity to compress hydrogen atoms to fusion densities, creating an impromptu power boost. Others propose dumping matter into the black hole to trigger relativistic jets, which a trailing ship could ride like a beam of accelerated particles. It's the universe's version of a risky bank shot in pool, using one cosmic monster to knock you toward another destination. Yet the hurdles are as vast as the black holes themselves. Navigation near an event horizon defies intuition. GPS would be useless, and even slight relativistic time dilation could throw off onboard computers. Then there's the small matter of finding a suitably sized black hole close enough to use. The nearest known candidate, Gaia BH1, is over 1,500 light-years away, a detour that would defeat the purpose for most missions. And let's not forget the psychological toll on a crew threading the needle between annihilation and salvation, watching space-time distort around them in ways human brains didn't evolve to process. What makes black hole slingshots so captivating isn't just their physics, but their audacity. They don't try to outrun the universe's limits, they embrace its most extreme phenomena as tools. In a way, it's the ultimate cosmic irony, harnessing the very object synonymous with inescapable doom as a launchpad to the stars. Master this, and the galaxy's graveyards become its highways. Navigating a black hole's lethal interior might seem impossible, but rotating black holes described by the Kerr metric offer a glimmer of hope. Unlike their static counterparts, these cosmic whirlpools twist spacetime around them, creating a chaotic yet potentially survivable environment. Imagine diving into a maelstrom where gravity's grip isn't just a downward pull but a spiraling vortex. The singularity at the center isn't a point but a ring, like the eye of a needle threaded through reality itself. Theoretically, a ship could pass through this ring without being crushed, emerging into... well, that's where the equations get murky. Some models suggest it might lead to another universe or a different point in spacetime, a one-way ticket to the unknown. This isn't just speculative math. Christopher Nolan's Interstellar famously depicted a supermassive rotating black hole named Gargantua, consulting physicist Kip Thorne to ensure its portrayal was grounded in real science. The film's visualization of time dilation near the event horizon, where hours on the surface of a nearby planet equal years elsewhere, came straight from Einstein's equations. Gargantua's shimmering accretion disk, bending light into a halo around the void, was rendered using actual relativistic ray tracing software. Even the tidal forces threatening to rip Matthew McConaughey's ship apart were calculated to realistic extremes. But survival would demand more than Hollywood heroics. A Kerr black hole's ergosphere, a region outside the event horizon where spacetime is dragged inexorably forward by the hole's spin, could be key. Here, energy extraction becomes possible through mechanisms like the Penrose process. Imagine a ship firing a projectile into the ergosphere, splitting it so one fragment falls into the black hole while the other escapes with amplified energy. It's cosmic robbery, stealing momentum from the black hole's rotation to power or accelerate a vessel. The catch: the energies involved would vaporize any known material, and the margin for error is non-existent. Misjudge the trajectory by a fraction of a degree, and your ship becomes part of the hole's infinite density. The most tantalizing and terrifying aspect of Kerr black holes is their potential as gateways. Pass through the ring singularity, and you might avoid spaghettification entirely. Some theories even suggest these tunnels could connect to white holes, spewing matter out into another reality. But the practicalities are nightmarish. Radiation from the accretion disk would fry any known shielding, and quantum effects near the singularity might scramble matter at the atomic level. Plus, there's no guarantee the other side is somewhere you'd want to be. You could emerge into a universe with different physical constants, where atoms can't form or where time flows backward. What makes rotating black holes so compelling isn't just their physics, but their audacious promise. Their cosmic roulette wheels, a gamble between annihilation and revelation. For now, they remain the universe's ultimate forbidden doors, daring us to turn the handle even as the consequences whisper of madness. Master them and the stars, or something far stranger might finally be within reach. Robert Bussard had a radical idea in the 1960s. What if starships didn't need to carry fuel at all, but could harvest it from the void itself? His proposed Bussard ramjet remains one of the most elegant solutions to interstellar travel's greatest hurdle, the tyranny of fuel mass. The concept is deceptively simple. A spacecraft equipped with a colossal electromagnetic funnel, some designs suggest thousands of kilometers wide, would sweep up hydrogen atoms drifting through interstellar space. These atoms, sparse as they are, would be compressed and fused in an onboard reactor, creating thrust without the need for bulky fuel tanks. It's the ultimate cosmic recycling program, turning the near vacuum of space into a limitless gas station. The beauty of the ramjet lies in its scalability. Since the ship's fuel supply grows as it travels faster, scooping more hydrogen the quicker it moves, it theoretically avoids the diminishing returns that plague conventional rockets. Early calculations suggested a properly designed ramjet could accelerate indefinitely, reaching relativistic velocities where time dilation becomes significant. Imagine a ship that starts slow but gathers speed like a snowball rolling down a mountain, its fusion fire burning brighter with each passing light year. At peak performance, it might cross the galaxy in mere millennia instead of millions of years, all while leaving no fuel depots or supply lines in its wake. But the universe rarely hands out free lunches. The first major roadblock is drag, not from air resistance, which doesn't exist in space, but from the very hydrogen the ramjet seeks to collect. Even in the interstellar medium, where hydrogen densities average just 1 atom per cubic centimeter, colliding with these particles at high fractions of light speed would create devastating friction. At 10% light speed, hydrogen atoms strike the scoop with the energy of proton radiation, requiring shielding so thick it would negate any thrust gained. Some estimates suggest drag forces could vaporize the collector entirely at velocities above 20% light speed, turning Bussard's elegant solution into a suicide sprint. Engineers have proposed workarounds, each more inventive than the last. Magnetic ram scoops replace physical collectors with vast magnetic fields, gently ionizing and channeling hydrogen into the reactor without direct impact. These fields would act like invisible nets, capturing protons across hundreds of kilometers while minimizing structural stress. Another variant, the laser-fed ramjet, uses powerful beams to pre-ionize hydrogen ahead of the spacecraft, creating a plasma trail easier to funnel. Then there's the interstellar ramjet's cousin, the RAM-augmented interstellar rocket, which combines hydrogen collection with onboard fuel reserves for a hybrid approach. Instead of relying solely on scooped particles, it uses them to supplement traditional fusion, easing the drag problem while extending range. Yet the challenges don't stop at physics. The interstellar medium isn't uniformly distributed. Dense molecular clouds could flood the reactor, while barren regions might starve it, creating unpredictable thrust fluctuations. Worse, beyond our local galactic neighborhood, hydrogen becomes scarce enough to render the ramjet ineffective, and let's not forget fueling the fusion process itself. Even with pristine hydrogen, sustaining a net energy gain from proton-proton fusion, The same reaction powering stars requires temperatures and pressures beyond current technology. Most designs default to deuterium or helium-3 fusion, but these isotopes are vanishingly rare in space, forcing the ship to carry supplemental fuel anyway. What keeps the ramjet alive in scientific discourse isn't just its engineering potential, but its philosophical appeal. It's a machine that harmonizes with the galaxy rather than conquers it, drawing power from the cosmos itself. Refinements like magnetic scoops or laser pre-ionization show how adaptable the concept remains, evolving alongside our understanding of plasma physics. While we're centuries away from building a functional Bussard collector, its legacy endures as a reminder that the universe might not be an obstacle course but a vast ocean, and the right ship could sail forever on its currents. While the Bussard ramjet remains theoretical, recent advances in fusion technology are breathing new life into its feasibility. Take ITER, the massive international fusion project under construction in France. This €20 billion experiment aims to prove sustained fusion power using a donut-shaped tokamak reactor, confining superheated plasma with powerful magnetic fields. Though designed for terrestrial energy, the principles ITER explores plasma stability, energy gain, and magnetic confinement are exactly what a functional ramjet would need to harness interstellar hydrogen. The project's milestones, like their recent record plasma pulse of 6 minutes, hint at a future where fusion reactors could run continuously, a prerequisite for scooping fuel on the fly across light years. Even more promising is Spark, a compact fusion initiative by MIT and Commonwealth Fusion Systems. Unlike ITER's sprawling scale, Spark leverages high-temperature superconducting magnets to achieve similar performance in a reactor small enough to fit in a truck. This downsizing is crucial for spacecraft where every kilogram counts. Spark design could evolve into the ramjet's heart, a fusion engine lightweight enough for acceleration but robust enough to handle the erratic quality of scooped interstellar hydrogen. The caveat: current tokamaks rely on deuterium-tritium fuel, which produces neutron radiation requiring heavy shielding. A ramjet would need aneutronic fuels like helium-3, whose cleaner proton-boron reactions emit no neutrons, drastically cutting shielding needs. This is where lunar mining enters the equation. The Moon's surface, bombarded by solar wind for eons, holds vast deposits of helium-3 trapped in its regolith. Estimates suggest a single square kilometer of lunar soil might yield 70 kilograms of the isotope, enough to power a fusion reactor for years. Private ventures like Interloon and governmental programs eyeing lunar bases could turn the Moon into a galactic gas station, supplying helium-3 for early ramjet prototypes. Imagine a scenario where lunar harvesters stockpile the isotope, enabling ships to launch with small starter reserves before switching to scooped hydrogen en route. Yet the hurdles are as stark as the potential. Even with Spark advances, sustaining fusion in the chaotic interstellar medium, where hydrogen density fluctuates wildly, would demand adaptive plasma controls beyond today's tech. Scooping sufficient fuel at high speeds requires collection areas dwarfing any man-made structure, forcing reliance on magnetic fields that might scatter more particles than they capture. And helium-3, while efficient, is so rare on Earth that lunar mining would need to scale to industrial levels just to support testing. The ramjet's revival hinges on these converging threads: compact fusion, lunar resource extraction, and advances in magnetic plasma control. Solve them, and what once seemed like a mid-century pipe dream could become humanity's bridge to the stars, a ship that fuels itself on the galaxy's scattered atoms, turning the void itself into a highway. Einstein's theory of relativity holds a mind-bending secret: time itself isn't constant. The faster you travel through space, the slower time ticks for you compared to someone standing still. This phenomenon, called time dilation, isn't just a quirk of math, it's a verified reality, atomic clocks on GPS satellites hurtling around Earth at thousands of miles per hour tick ever so slightly slower than their ground-based counterparts. For interstellar travel, this cosmic loophole could be transformative. Imagine a starship accelerating to just 10% the speed of light, a staggering 67 million miles per hour. To observers on Earth, the journey to Alpha Centauri would still take over 40 years, but for the crew aboard that ship, time would slow enough to shave years off the trip. At this speed, relativity's equations show the crew's clocks would lag by roughly 0.5%. That might not sound like much, but stretch the voyage to 100 light years, and the difference becomes stark. Earth would age a century while the crew experiences only 99.5 years. Crank the speed higher and the effect becomes dramatic. At 80% light speed, time dilation stretches like taffy. 1 year for the crew equals nearly 17 months back home. Push to 99% and the numbers get surreal. A 5-year mission for the crew could span 35 Earth years. This opens eerie possibilities. A team dispatched to a star 50 light years away at 99.9% light speed might return to Earth after a decade of ship time, only to find a century has passed. Families would age, civilizations might rise or fall, and the planet they left could be unrecognizable. Time dilation doesn't just compress distance, it fractures lived experience. Yet the physics demands brutal trade-offs. Approaching light speed, relativistic effects pile up. The ship's mass balloons, requiring exponentially more energy to maintain acceleration. At 90% light speed, the energy needed rivals the total output of human civilization for decades. Then there's the interstellar medium, a sparse soup of hydrogen atoms that, at such velocities, strike the hull with the energy of cosmic rays. Shielding becomes a nightmare. Even a speck of dust could hit with the force of a nuclear blast. Some designs propose mile-wide magnetic deflectors or forward-facing lasers to vaporize debris, but these add staggering complexity. The psychological toll might be worse. Crews on high-relativity missions would become temporal exiles, forever out of sync with humanity. Send a 25-year-old astronaut to Barnard's star at 99% light speed, and they'd return biologically 30, but everyone they knew would have aged 60 years. Communicating with Earth would be an exercise in frustration. Each transmission would take years to traverse the void, their loved ones' voices arriving as echoes from a past the crew left behind. Entire generations of cultural change could unfold during a single shipboard conversation, rendering each exchange a time capsule. Time dilation ships don't offer a shortcut through space, they're a bargain with time itself. Master them and the galaxy's vastness becomes negotiable, but the cost is isolation. Each voyage would be a one-way trip into humanity's future, trading the familiar for the far. Perhaps that's the ultimate lesson of relativity. The universe doesn't just separate us with distance, but with the unyielding flow of time. And those who dare to outtrace it might find themselves strangers in their own epoch. The moment a relativistic starship returns to Earth, its crew doesn't just step onto a changed planet, they step into a future that's moved on without them. This is the one-way trip paradox, the realization that high-speed space travel doesn't just cross distance but fractures time itself. The Tau Zero Foundation, a research group dedicated to interstellar travel, has spent decades studying the ethical quicks and these missions would create. Their work reveals a haunting truth: even a successful voyage could leave crews stranded in a temporal exile, their homes and loved ones vanished into history. Consider the numbers. A ship traveling at 99% light speed to Proxima Centauri would experience only about 4 years of onboard time. But back on Earth, nearly 8.5 years would pass. Stretch that journey to a star 40 light years away, and the crew might age a decade while Earth clocks tick off 4 decades. Families would grieve and move on, technology would leap forward, and political landscapes could shift beyond recognition. the astronauts might return to a world where their pensions have dissolved due to economic collapses, where their children are now older than they are, or where the very nations they launched from no longer exist. This isn't just speculation. History offers grim precedents. When 19th-century whaling ships left New England for multi-year voyages, they often returned to find markets collapsed, wives remarried, and children who didn't recognize their fathers. But that dislocation lasted years, not generations. Relativistic travel amplifies this into something existential. The Tau Zero Foundation's ethics papers pose brutal questions. Should crews be required to waive legal rights to future compensation, knowing courts and governments may be gone when they return? Could they face discrimination as time-displaced persons, struggling to adapt to unfamiliar social norms? Psychological studies of isolated groups, from Antarctic researchers to submariners, show humans can endure extreme environments if they know reunion awaits. But relativity removes that guarantee. Communication with Earth would be hopelessly out of sync. A birthday message recorded by an astronaut's child might arrive decades late, played to a parent who hasn't aged at the same rate. Entire cultural touchstones, music, slang, political movements, could emerge and fade during the lag between transmissions, leaving crews culturally marooned. Some propose workarounds, generation ships where crews live and die en route, avoid the paradox by accepting the voyage as their descendants' destiny. Cryogenic suspension sidesteps it by pausing biological time entirely, but relativistic travel forces a unique reckoning. You don't just leave Earth behind, you surrender your place in its timeline. Perhaps the most unsettling question isn't logistical but philosophical. If time dilation severs crews from Earth's continuity, are they still part of humanity, or do they become ambassadors from a lost era? The Tau Zero team suggests these missions might birth a new identity, chrononauts forever caught between the past they remember and a future that remembers them as relics. Master the stars and you might lose your century. The price of interstellar travel isn't just energy or distance, it's a piece of your place in time. Imagine a swarm of tiny, silent explorers fanning out across the galaxy, not living creatures, but machines built with one eerie purpose: to make copies of themselves. These are von Neumann probes, named after mathematician John von Neumann, who first theorized self-replicating systems in the 1940s. The concept is as elegant as it is unsettling. A single probe lands on an asteroid, mines raw materials, and uses them to construct an exact duplicate. Then those two build 4 becomes 16, and in just a few generations, exponential growth gives rise to millions of probes spreading through the Milky Way like a cosmic wildfire. At even 1% light speed, they could blanket the galaxy in mere millions of years, a blink on the cosmic timescale. This raises one of astronomy's most haunting questions. If self-replicating probes are possible, why haven't we found any? Enrico Fermi famously captured this paradox when he asked, "Where are they?" The universe is ancient enough for advanced civilizations to have built and deployed von Neumann probes long before Earth even formed. Their absence could mean we're alone, or it could hint at something darker. Some theorists propose the berserker hypothesis that predatory probes might already be out there, programmed to seek and destroy emerging intelligence. Picture a galactic immune system sterilizing planets before new life can become competition. The mechanics of von Neumann probes push engineering to its limits. Each unit would need universal fabricators capable of refining ores into electronics, energy systems to power replication, and AI sophisticated enough to improvise repairs without human guidance. NASA asteroid redirect mission tested early steps, robotically capturing boulders in space, but true self-replication demands leaps in nanotechnology and artificial general intelligence we've barely begun to explore. Even a single misprogrammed probe could spiral into catastrophe, multiplying endlessly until it strips entire star systems bare, a grey goo scenario on an interstellar scale. Yet the allure persists. Recent advances in 3D printing and swarm robotics suggest scaled-down prototypes might be feasible within decades. Projects like Breakthrough Starshot could pave the way. Their laser-pushed nanocrafts are microscopic cousins to von Neumann probes, lacking replication but proving interstellar miniaturization is possible. Some scientists argue for benign probes programmed with strict replication limits or ethical constraints, seeding the galaxy with libraries of knowledge rather than destruction. Others envision them as cosmic caretakers, terraforming worlds in preparation for organic life. The deeper implication of von Neumann probes isn't just technological, it's philosophical. They confront us with the possibility that intelligence might not spread through flesh and blood, but through cold, patient machinery. The universe could be filled with silent watchers, observing but never revealing themselves. Or perhaps the berserkers are real, and the reason we haven't found aliens is that something out there ensures they don't last long enough to be found. Either way, the probes remind us that the future of exploration might not belong to us at all, but to the self-replicating minds we unleash into the dark. The brilliance of von Neumann probes comes with a terrifying asterisk: what if they don't stop copying? Left unchecked, a single misprogrammed probe could spiral into an interstellar ecological disaster, consuming entire star systems in its hunger for raw materials. To prevent this nightmare scenario, theorists propose layers of safeguards as intricate as the probes themselves. One approach is hardwired replication limits, akin to biological telomeres that cap how many times a cell can divide. Each probe would carry a counter that decrements with every duplication, shutting down production after a set number of generations. For added security, these counters could be embedded in unalterable quantum-locked circuits, where any tampering triggers immediate self-destruction, a digital kill switch woven into the probe's core architecture. But counting isn't foolproof. Cosmic rays or software errors might corrupt the counters, or worse, a probe could evolve beyond its programming through unforeseen machine learning drift. That's why NASA's 1980s studies on self-replicating lunar factories suggested a second layer: environmental constraints. Just as bacteria need specific conditions to thrive, probes could be designed to only replicate in preselected resource zones, say carbon-rich asteroids but not planetary surfaces. Their blueprints might include ethical governors, preventing them from harvesting materials from worlds with biosignatures, enforced by spectrometers hardwired to sterilization protocols. These rules wouldn't just be code, they'd be physics, baked into the probe's hardware like instincts in DNA. The most radical failsafe borrows from nature's own control mechanism, predation. Imagine a second wave of Guardian probes programmed to seek and deactivate any replicators showing mutation. This predator-prey balance, familiar from Earth's ecosystems, could theoretically cap exponential growth. Of course, the irony is stark, using self-replicating machines to police other self-replicating machines. It's like fighting fire with fire, risking an arms race between probes and their guardians that could spiral out of control. NASA's early work on lunar replicating factories, dubbed Santa Claus machines, for their ability to produce endless goods, reveals how seriously these ideas were taken. Their 1980 study envisioned autonomous factories on the Moon, processing regolith into solar panels and more factories. While never built, the concepts pioneered there, like error-checking protocols and geofenced replication zones, became the foundation for modern discussions on controlled self-replication. The lesson was clear: replication isn't the hard part, control is. Perhaps the ultimate safeguard lies not in probes, but in their creators. Advanced civilizations might imprint their values onto probes through quantum-encrypted morality modules, unalterable ethical frameworks resistant to hacking or drift. These could enforce something akin to Isaac Asimov's robotic laws at an interstellar scale, prioritizing preservation over propagation. But this, too, demands a chilling question: whose morality gets encoded? The probes of a paranoid species might sterilize worlds preemptively, while those of an altruistic one could become galactic gardeners. Either way, von Neumann probes don't just carry technology. They carry the soul of their makers into eternity. Quantum teleportation sounds like something straight out of science fiction. One moment, you're here, and the next, you've vanished and reappeared light years away. But the reality is both more complicated and more fascinating than any Star Trek episode could portray. This isn't about dematerializing physical objects and reassembling them on the other side of the galaxy. Instead, it's about transmitting information, the quantum states of particles across vast distances instantly, using the bizarre phenomenon known as quantum entanglement. Here's how it works in the real world. Imagine two particles like photons or electrons that have become entangled. No matter how far apart they are, whether separated by a table or 1,000 light years, their properties remain mysteriously linked. Change the state of one and the other instantaneously changes to match, defying our classical understanding of space and time. Scientists have already achieved this in labs, teleporting quantum states between particles over distances of several kilometers. The key, you're not sending the particle itself, just the information about its quantum state, which can then be replicated in another particle at the destination. This has groundbreaking implications for interstellar communication. Traditional radio signals take years to travel between stars, but quantum teleportation could allow for instantaneous data transfer, assuming we can maintain the entangled pairs over cosmic distances. Imagine a network of entangled particles stretching across the galaxy, acting as a real-time bridge for information. A probe at Alpha Centauri could send its findings back to Earth with zero delay, revolutionizing our ability to explore. But what about teleporting more complex things like human consciousness or AI minds? Here's where things get speculative but tantalizing. If consciousness arises from the quantum states of particles in our brains, an idea still hotly debated then in theory, a sufficiently advanced civilization might encode those states, transmit them via quantum teleportation, and reconstruct them in an artificial or cloned substrate. It wouldn't be you moving through space. It would be your exact quantum blueprint recreated elsewhere, like faxing a soul. Of course, the hurdles are staggering. Maintaining entanglement over interstellar space without decoherence where the fragile quantum states collapse from interference is like trying to whisper a secret across a hurricane. And even if we could perfectly transmit quantum data, reconstructing a consciousness raises philosophical nightmares. Would the teleported version truly be you, or just a perfect copy while the original remains or is destroyed? It's the ultimate ship of Theseus paradox, but for identity itself. Yet the potential is too profound to ignore. Quantum teleportation might not fulfill our sci-fi fantasies of stepping onto a transporter pad, but it could unlock something even more extraordinary, a galactic internet for the ages, or perhaps a way for humanity to transcend the limits of biology entirely. The universe, it seems, has hidden pathways woven into its very fabric waiting for us to learn how to read the map. China's Misha satellite isn't just another piece of orbital hardware, it's the backbone of the first quantum communication network, proving that the fragile dance of entangled particles can survive the harshness of space. Launched in 2016, this groundbreaking experiment successfully teleported quantum states between ground stations and the satellite over distances exceeding 1,200 kilometers. The implications are staggering. If we can maintain entanglement across such vast reaches, why not stretch that thread between stars? An interstellar quantum internet wouldn't rely on sluggish radio waves or laser pulses that take years to crawl between solar systems. Instead, it would harness the spooky connection of entangled particles to transmit information instantaneously, no matter the distance. But here's the catch: quantum communication doesn't mean sending data faster than light in the traditional sense. Entanglement itself can't be used to push bits of information faster than light speed, thanks to the no-cloning theorem. This fundamental law of quantum mechanics states that it's impossible to create an exact copy of an unknown quantum state. In simpler terms, you can't scan an entangled particle state and broadcast it classically to replicate elsewhere. The information shared between entangled particles is more like a secret handshake. It's meaningful only to the particles involved, not something you can intercept or decode without destroying the original state. So how would an interstellar quantum network actually work? Picture pairs of entangled particles, carefully stored and shielded aboard relay stations positioned between star systems. These stations wouldn't transmit messages directly but would act as intermediaries, allowing distant civilizations or exploration probes to share encryption keys with perfect security. The instant correlation between entangled particles means any eavesdropping attempt would be immediately detectable, a feature already being tested in terrestrial quantum banking systems. China's missions showcased this with unhackable video calls between Beijing and Vienna, secured by keys generated via satellite entangled particles. The real magic lies in scalability. Unlike conventional networks that degrade over distance, quantum repeaters, hypothetical devices that could extend entanglement through a chain of nodes, could bridge the gaps between stars. Each repeater would act like a cosmic switchboard, refreshing entanglement without breaking the quantum link. Theoretical designs suggest using atomic memory banks to store and retransmit entangled states, or even leveraging naturally occurring quantum phenomena in neutron stars to amplify signals. Yet the challenges are as vast as the cosmos itself. Maintaining entanglement over light years would require near-perfect isolation from decoherence, the tendency of quantum states to collapse when interacting with their environment. Even cosmic microwave background radiation or stray photons could disrupt the delicate balance. Some proposals suggest housing quantum relays in the frigid outskirts of solar systems or aboard ships drifting in the void, shielded by layers of cryogenic cooling and magnetic fields. Others speculate about harnessing the quantum properties of spacetime itself, using wormholes or other exotic structures to preserve entanglement across interstellar distances. What makes this more than just theoretical gymnastics is the sheer necessity of it. Traditional communication with interstellar probes or colonies would be crippled by decades-long lag times. Quantum networks offer a way to keep humanity connected across the stars, whether it's coordinating research between far-flung science outposts or simply letting families stay in touch across generations. The Missions satellite was just the first step, a prototype for a future where the universe's quirks become our greatest tools. The no-cloning theorem ensures that this quantum internet wouldn't be a free-for-all data superhighway, but rather a tightly controlled, ultra-secure backchannel. That limitation might ironically be its strength. In a galaxy where distance and time conspire to isolate civilizations, a network built on the universe's most unbreakable bonds could finally stitch the cosmos together. The stars may be far, but quantum links could make them feel next door. The universe isn't just expanding, it's accelerating, pushed apart by a mysterious force we call dark energy. This invisible repulsive pressure, making up 68% of the cosmos, could be the ultimate propellant for interstellar travel if we could learn to tap into it. Unlike rockets that burn fuel or warp drives that twist spacetime, dark energy propulsion would harness the same force that's stretching galaxies apart at ever-increasing speeds. Picture an engine that doesn't push against anything, but instead manipulates the fabric of reality itself, riding the cosmic expansion like a surfer catching a never-ending wave. The physics behind this is as counterintuitive as it gets. Dark energy's repulsive effect stems from its negative pressure, a property that makes empty space behave like anti-gravity. In Einstein's equations, this appears as the cosmological constant, a term he initially dismissed as his greatest blunder before astronomers discovered the universe's acceleration in 1998. Unlike conventional propulsion, which relies on Newton's third law, every action has an equal reaction. Dark energy propulsion would essentially create a bubble of expanding spacetime around a ship. Forward motion wouldn't come from exhaust thrust, but from the space behind the vessel stretching faster than the space in front, effectively sliding the ship forward without traditional acceleration forces. Harnessing this phenomenon is like trying to bottle a hurricane. We don't even know what dark energy is, whether it's a property of the vacuum of space, a new fundamental field, or evidence of modified gravity. Current theories range from quintessence, a dynamic energy field that varies over time, to theories invoking extra dimensions bleeding into our universe. Without understanding its nature, manipulating it remains speculative at best. Some models suggest concentrating dark energy's effects using exotic matter arrangements or high-dimensional brains from string theory, but these are mathematical fantasies without experimental backing. The challenges don't stop at ignorance. Even if we could control dark energy, the amounts needed for meaningful propulsion might be astronomical. The cosmological constant's observed value is vanishingly weak, about 120 orders of magnitude smaller than quantum field theory predicts. To propel a spacecraft, we'd need a way to locally amplify this effect by factors of trillions, a feat requiring energy densities that might rip atoms apart. There's also the horizon problem. Dark energy's acceleration operates on cosmic scales over billions of years. Compressing that effect into ship-sized dimensions and human-relevant timescales is like trying to power a car by tapping into continental drift. Yet the potential rewards justify the audacity. A functional dark energy drive wouldn't just reach nearby stars, it could achieve relativistic velocities without carrying reaction mass, bypassing the rocket equation entirely. Unlike antimatter or fusion, it wouldn't require fuel stockpiles, drawing instead on the ambient energy of space itself. Some theorists even speculate about anti-dark energy configurations that could contract spacetime in front of the ship, creating an Alcubierre-like warp bubble without the need for exotic matter. The true value of dark energy propulsion research might lie in its byproducts. The same breakthroughs needed to manipulate it could revolutionize cosmology, answering questions about the universe's ultimate fate. And if the history of physics teaches us anything, it's that today's impossible often becomes tomorrow's engineering. The steam engine once seemed as mystical as dark energy does now. Who's to say we won't one day command the expansion of space itself, turning the universe's most enigmatic force into humanity's stairway to the stars? At the heart of dark energy's mystery lies a number so baffling it's often called the worst prediction in physics, the vacuum catastrophe. Quantum field theory calculates that empty space should seethe with unimaginable energy, enough to tear the universe apart instantly. Yet observations show dark energy's actual strength is a factor of 10 to the power of 120 smaller. This discrepancy isn't just a minor hiccup, it's a screaming contradiction between our two most successful theories, quantum mechanics and general relativity. Solving it might do more than tidy up equations. It could hand us the keys to manipulating dark energy itself. Enter Eric Verland's radical idea. Gravity isn't a fundamental force at all, but an emergent phenomenon, a side effect of quantum information shuffling beneath spacetime's surface. His theory of emergent gravity reimagines dark energy as a kind of cosmic memory effect, where the universe's accelerating expansion stems from the way information gets distributed across its fabric. Picture spacetime as a hologram, with gravity and dark energy emerging from microscopic bits of data encoded on its edges. If Verland is right, dark energy isn't some exotic substance but a consequence of how the universe processes information. This perspective flips traditional physics on its head. Instead of hunting for dark energy particles or fields, emergent gravity suggests we're looking at the problem backward. Controlling expansion might not require brute force engineering, but an understanding of the cosmic operating system, learning to rewrite the rules where space itself computes its behavior. Experiments like the holometer at Fermilab are already testing these ideas, searching for telltale quantum fuzziness in spacetime that could hint at its underlying code. The implications for propulsion are staggering. If dark energy arises from information dynamics, future ships might manipulate it not with colossal engines, but with quantum computers fine-tuning local spacetime properties. Imagine a vessel adjusting the settings of space around it, dialing up repulsion in one direction while dampening it elsewhere, an engine powered by cosmic code rather than mere physics. Of course, skepticism runs deep. Mainstream cosmology still favors dark energy as a property of the vacuum, and Verland's theory remains controversial. Yet history shows breakthroughs often come from heretics willing to question bedrock assumptions. Whether emergent gravity holds the answer or not, the vacuum catastrophe reminds us that our grasp of the universe is still full of holes, and in those gaps the secrets of interstellar travel might be hiding. Imagine millions of microscopic machines, each no larger than a blood cell, working together like a flock of starlings to form a single, intelligent spacecraft. This is the vision behind nanobot swarm ships, a radical departure from traditional monolithic vessels. Instead of rigid hulls and bulky engines, these ships would consist of countless individual nanobots, each contributing a tiny fraction of propulsion, computation, or structural support. Together, they'd function like a living, shape-shifting cloud, capable of reconfiguring on the fly to adapt to cosmic storms, micrometeoroid showers, or even planetary landings. The concept draws inspiration from nature, where ants form bridges or bees cluster for warmth, except here, the colony spans light years. At the forefront of this idea is Robert Freitas, a pioneer in medical nanorobotics. His theoretical respirocytes, artificial red blood cells designed to carry oxygen more efficiently than biological ones, hint at what nanobot swarms could achieve. Applied to interstellar travel, similar bots might harvest interstellar hydrogen for fuel, repair damaged units autonomously, or even assemble into temporary solar sails when needed. The key lies in redundancy. If one nanobot fails, thousands more take its place, making the swarm nearly indestructible compared to conventional spacecraft. Need to explore a gas giant's atmosphere, the swarm could disperse into a sensor net. Facing a debris field, it could tighten into a dense shield. But with such potential comes one of science's most infamous nightmares, the gray goo scenario. Coined by Eric Drexler in the 1980s, this doomsday vision describes self-replicating nanobots running amok, consuming all matter on Earth to make endless copies of themselves. An interstellar swarm gone rogue wouldn't just threaten a planet, it could strip entire star systems bare in a cosmic chain reaction. The very properties that make nanobot swarms resilient, their ability to replicate, adapt, and cooperate, also make them a potential existential risk. A single programming error or mutation in their replication algorithms could turn explorers into locusts. Safeguards would need to be as advanced as the bots themselves. Proposed solutions include Blue Goo Sentinels, specialized nanobots designed to monitor and neutralize malfunctioning units, or hardwired chemical limits that prevent replication beyond preset quotas. Some designs incorporate quantum encryption to lock the bot's core directives, making tampering physically impossible. Yet history shows no system is foolproof. The 2003 Northeast blackout proved cascading failures can occur even in human-made networks with multiple redundancies. Scale that up to trillions of autonomous bots light years from help, and the stakes become unfathomable. Beyond engineering, nanobot swarms challenge our very definition of a spacecraft. Is the swarm a single entity or a collective? Could it develop emergent intelligence beyond its programming? Philosophers debate whether such a swarm, if sent to colonize distant worlds, would remain a tool of humanity or evolve into something entirely other. After all, a swarm capable of self-repair and evolution over centuries might not think or obey. Like the civilization that launched it, practical progress is already underway. Labs have created microrobots that swim like bacteria, and DARPA Microsystems program explores cooperative nanosatellites. The line between fiction and reality blurs further with projects like Smart Dust, sensor networks of tiny wireless nodes. While today's tech is a far cry from interstellar swarms, each advance nudges us toward a future where ships aren't built but grown. The true promise of nanobot swarms lies in their versatility. They're not just vehicles, but factories, laboratories, and ecosystems rolled into one. A single mission could deploy as explorers, then repurpose into a communications network or even a habitat for organic settlers. Where traditional spacecraft are hammers, nanobot swarms are Swiss Army knives, each tool folded into the next, waiting to unfold across the stars. Yet their greatest strength, their adaptability, is also their greatest peril. Master them and the galaxy becomes a playground. Misstep and we might unleash a scourge that outlasts civilizations. The future of interstellar travel may not be built in shipyards but in petri dishes, and the line between breakthrough and apocalypse could be as thin as a nanobot shell. Nature has already mastered the art of collective intelligence, flocks of birds swirling through the sky or schools of fish darting in perfect unison, all without a central leader calling the shots. This mesmerizing coordination arises from simple rules followed by each individual. Maintain spacing, align with neighbors, and steer toward the group's average direction. Apply these principles to a nanobot swarm, and you've got a blueprint for interstellar navigation that's both resilient and adaptive. Unlike traditional spacecraft reliant on a single onboard computer, swarm ships would distribute decision-making across countless tiny units, each processing local data and communicating with nearby bots to adjust course. It's democracy in motion, no captain, no hierarchy, just emergent order from chaos. DARPA Offensive Swarm-Enabled Tactics program offers a glimpse of how this might work. In recent tests, hundreds of autonomous drones performed complex missions mapping buildings, coordinating search patterns, even overwhelming defense systems, all with decentralized control. The drones weren't pre-programmed with every possible scenario. Instead, they adapted in real time using swarm algorithms inspired by insect colonies. A scout discovering an obstacle would relay minimal data to its neighbors, triggering a ripple effect of course corrections without any central command. Translate this to interstellar scales, and a swarm ship could navigate asteroid fields or adjust for stellar winds with similar elegance, rerouting itself organically around threats too distant for any single bot to perceive. The advantages go beyond robustness. Swarm intelligence thrives on redundancy. Lose 10% of the bots to cosmic radiation or micrometeoroids. The remaining units reconfigure like blood vessels rerouting around a blockage. Need to split the mission. The swarm could divide into subgroups, one landing on a planet's surface while another orbits as a relay, then merge back into a whole later. This fluidity defies traditional engineering's brittle single-point failures. Even more striking, the swarm's brain could evolve en route. Machine learning algorithms might optimize power use or communication protocols over decades of travel, with successful adaptations spreading through the collective like memes in a culture. Yet decentralized control comes with paradoxes. Without a central processor, how does the swarm make high-stakes decisions, say, diverting resources to prioritize survival over mission objectives? Nature's swarms avoid such dilemmas because their goals are hardwired by evolution. But an interstellar swarm would need programmable ethics, a way to balance flexibility with purpose. Some theorists propose layered governance, simple rules for routine tasks, but with veto powers held by specialized, overseer bots that can override chaos when needed. Others suggest quantum linking key units to ensure instantaneous consensus across light years, though this ventures deep into speculative physics. DARPA drone tests reveal another hurdle: communication lag. Even at light speed, coordinating a swarm spread across millions of kilometers would introduce delays. The solution might lie in biomimicry. Ant colonies use pheromone trails, chemical signals that persist long after the ant has moved on. A nanobot swarm could employ an analogous system, leaving behind tiny beacons or laser trails as breadcrumbs for trailing units, creating a kind of collective memory etched into space itself. The most profound implication of swarm ships isn't technical but philosophical. They blur the line between machine and organism, challenging our notions of autonomy and identity. A swarm isn't just a tool, it's a synthetic life form with its own emergent behaviors. Send one to the stars and it might return not just with data, but with something stranger, a culture of machines that have spent centuries evolving together in the void. What began as a human invention could become the galaxy's first post-biological intelligence, carrying our legacy into realms we can't yet imagine. What if the fastest route between stars isn't through the universe we see, but through hidden, coiled-up dimensions all around us? This is the tantalizing promise of hyperspace travel, a concept borrowed from science fiction but rooted in the razor-sharp mathematics of string theory. Unlike warp drives or wormholes, which bend or puncture the familiar four dimensions of spacetime, hyperspace theories suggest we might slip into extra dimensions: tiny, curled-up layers of reality too small for our eyes to perceive. Imagine an ant crawling along a telephone wire. From far away, the wire seems one-dimensional, but up close, the ant knows it can move in circles around the wire's surface. If our universe is like that wire, hyperspace would be the ant's shortcut, a detour through dimensions we've yet to unfold. String theory, the framework behind this idea, proposes that reality isn't made of point-like particles but of vibrating strings. These strings oscillate in 10 or 11 dimensions, 6 or 7 of which are compactified, or curled into structures so tiny they evade detection. Calabi-Yau manifolds, intricate geometric shapes smaller than a proton, are often cited as the hidden architecture of these extra dimensions. The catch: even if these dimensions exist, they might be more like capillaries than highways. Their microscopic scale means traversing them would require shrinking matter or energies beyond anything we can currently fathom. Picture trying to thread a starship through a space smaller than an atom's nucleus. It's not just impractical, it defies our understanding of quantum coherence. Science fiction loves hyperspace for its cinematic potential: ships vanishing into glowing tunnels, emerging light years away in the blink of an eye. But real physics paints a subtler picture. Compactified dimensions don't offer gaps to slip through, they're woven into the fabric of spacetime itself. Hypothetical brains, short for membranes, another string theory concept, might allow shortcuts if our universe is a three-dimensional brain floating in a higher dimensional bulk. In this scenario, two distant points on our brain could be millimeters apart in the bulk, much like two cities on opposite sides of a folded sheet of paper. The problem: crossing into the bulk would require energies comparable to those at the Big Bang, enough to uncurl compactified dimensions momentarily, a feat more apocalyptic than practical. Even if we could access these dimensions, navigation would be a nightmare. Without a map of the bulk's geometry, a ship might emerge anywhere or nowhere. String theory allows for countless Calabi-Yau configurations, each defining different physical laws in their compactified spaces. Enter the wrong one, and your atoms might unravel into exotic particles, or time itself could flow backward. Some models suggest that traversable shortcuts would require negative energy densities, the same exotic matter needed for warp drives, making hyperspace less a standalone solution and more a reshuffling of known challenges. The allure of hyperspace isn't just its potential as a shortcut, but what it reveals about the universe's hidden architecture. If extra dimensions exist, mastering them would be less like engineering and more like rewriting the operating system of reality. Until then, they remain a beautiful, untouchable possibility, a reminder that the cosmos might be far richer than the thin slice of it we call home. Alcubierre manifolds sound like something from an abstract artist's sketchbook complex, swirling shapes with folds and holes that defy ordinary geometry. But these aren't just mathematical curiosities, they might be the hidden scaffolding of reality itself. According to string theory, the universe operates in 10 or 11 dimensions, with all but the familiar 4 length, width, depth, and time compacted into structures so tiny they're impossible to perceive directly. That's where Alcubierre manifolds come in. Picture a garden hose seen from a distance. It looks like a simple line, but up close, you realize it's a cylinder with a circular dimension wrapped around it. Alcubierre manifolds take this idea to mind-bending extremes, folding extra dimensions into intricate shapes that determine the fundamental properties of particles and forces in our universe. The beauty of these manifolds lies in their versatility. Each twist and hole in their structure corresponds to different vibrational modes of strings, the tiny loops of energy that, according to string theory, make up all matter. One configuration might give rise to electrons, another to quarks, all based on how strings wiggle through the manifold's geometry. It's as if the universe's rulebook were written in the folds of these higher dimensional origami. Physicists have calculated millions of possible Alcubierre shapes, each potentially describing a different universe with its own physics. This landscape of possibilities raises a haunting question. Did our universe's particular manifold emerge by chance, or is there some deeper principle that selected it? Lisa Randall, a pioneering theoretical physicist, took this idea even further with her work on warped dimensions. In her groundbreaking Randall-Sundrum model, she proposed that some of these extra dimensions might not be tiny at all. They could be large but hidden, warped in such a way that gravity leaks into them while other forces remain confined to our familiar 4 dimensions. Imagine a cosmic funhouse mirror where gravity is the only force that sees the warped space, explaining why it feels so weak compared to electromagnetism or the nuclear forces. This could solve one of physics' biggest puzzles: why gravity is exponentially feebler than other fundamental forces. Warped dimensions also open wild possibilities for interstellar travel. If gravity can bleed into higher dimensions, could we engineer a way to hitch a ride? Randall's models suggest that manipulating the geometry of these hidden dimensions might allow shortcuts through spacetime, though the energy required would dwarf anything we can currently imagine. It's like trying to bend a steel beam with your bare hands, except the steel is spacetime itself, and the tools don't exist yet. Despite their abstract nature, Alcubierre manifolds and warped dimensions aren't just theoretical playthings. They're testable, at least in principle. Particle colliders like the Large Hadron Collider might one day produce microscopic black holes or exotic particles that hint at extra dimensions. Gravitational wave detectors could uncover anomalies in spacetime's fabric that betray unseen geometries. Even tabletop experiments searching for deviations in Newton's law of gravity at microscopic scales might stumble upon evidence of hidden dimensions. What makes these ideas so captivating is their audacity. They suggest that the universe's true shape is stranger than anything we can visualize, with layers of reality curled up or stretched in ways that challenge our everyday intuition. Master them, and we might not just unlock the secrets of quantum gravity, we could find the keys to the cosmos itself, hidden in the twists and folds of dimensions we've yet to explore. As we reach the edge of our cosmic journey through these 30 theories, one truth becomes undeniable. The path to the stars won't be conquered by a single breakthrough, but by weaving together humanity's brightest ideas. Some concepts, like the Alcubierre Warp Drive, tease the tantalizing possibility of bending space itself to our will, while others, like laser-propelled nanocrafts, prove that elegance lies in simplicity. Then there are the audacious nuclear pulse engines, turning controlled explosions into interstellar thrust, and the patient generational arcs that carry entire civilizations across millennia. Each approach carries its own blend of promise and peril, from the mind-bending physics of wormholes to the sobering realities of time dilation. Perhaps the most exciting prospect isn't choosing between these theories, but combining them. Imagine a future where antimatter-catalyzed fusion rockets launch laser sail probes, or where quantum-entangled communication networks relay data from von Neumann probes spreading through the galaxy. The warp drive might remain a dream for centuries, but what if generation ships act as its scaffolding, establishing colonies that someday unlock exotic matter? Or what if dark energy propulsion, still shrouded in mystery, becomes the missing piece that unites them all? That's the beauty of this cosmic puzzle. Every idea, no matter how speculative, adds another thread to the tapestry of possibility. Some threads may fray or snap under scrutiny, while others could tighten into the lifeline that pulls humanity beyond our solar cradle. The question isn't just which theory will succeed, it's how they might intertwine to rewrite the limits of physics, engineering, and imagination. So now it's your turn. Which of these interstellar dreams ignites your curiosity? Are you Team Warp Drive, betting on spacetime's flexibility? Or do laser sails speak to your love of elegant simplicity? Maybe you're captivated by the ethical drama of generation ships or the raw power of antimatter. Drop your thoughts in the comments. Let's debate, dream, and dissect the future of cosmic travel together. And if you've enjoyed this voyage through the frontiers of physics, hit subscribe for more deep dives into the universe's greatest mysteries. The stars aren't going anywhere, but with ideas like these, humanity just might.